Hello and welcome to another one of D's ADD videos. Today we're going to be looking at SN2 reactions, what to do and how to do it. First thing you should do is recognize what makes it an SN2 reaction. Well, a couple things make it an SN2 reaction. One is the attacking species. In this case, our attacker has to be a strong attacker. So we have to have some sort of alkoxide ion or something along those lines. And it should be small so it can do a backside attack. If it's too big, then we're going to end up with an E2 reaction, what's known as a Hoffman product, and you can watch that video later on. Okay, so what are the steps for this? Because it's an SN2 reaction, what happens is it's a concerted reaction. It occurs all in one step. The nucleophile starts forming a bond right when it starts breaking the bond with the leaving group. Okay, and once the leaving group leaves, that means the nucleophile now has been attached and the stereochemistry has been inverted. So if we go over here and we look at this wonderful compound here, assigning priority based on atomic number. Oops, that was too big. Let's try that again. This would be 1. Carbon and carbon is a tie, but then there's an extra carbon here, so that's the tiebreaker. Then 3, so this is counterclockwise, and S, because the hydrogen's into the page, you don't need to flip it. So we have an S stereochemistry here, and hopefully when we're done we should have O stereochemistry. And I made a mistake, didn't I? No, I didn't. This is a strong attacker. I think I just wanted to use sodium hydroxide to begin with, but I ended up using the methoxide ion, it looks like, so which is fine, we can do that as well. In this case, what's going to happen is this methoxide ion is going to come on the opposing side of your leaving group, and it starts to form a bond and break this bond instantly. It's a concerted reaction, and that would be your transition state. I guess I'm being kind of lazy and not writing it on the next step, but it would look something like this. So we then let the leaving group go about its merry business, and we are left with actually the minus sign is no longer there because it's going to be bound to the carbon. I now have 2 lone pairs above and below, which make it neutral. And I guess I should draw some stereochemistry here. So this is still wedged out at you. This is going into the page now. And now we have 1, 2, 3 priority. That's clockwise, and therefore it's R. So there's an inversion taking place. Okay. So remember with these things that you want the smaller the substrate, the better. Methyl primary, secondary, but tertiary, no. All right. It's called steric hindrance. The electron density of your electrophile is too bulky and will not allow your nucleophile to attack. You guys remember the difference between electrophile? The carbon that had the leaving group attached to it had a plus charge on it, so it likes electrons, so therefore it's called an electrophile. And the attacker in this case, the alkoxide or the methoxide ion, is electron rich, but so is a base. What differs between that and a base? Well, this will attack the actual carbon, whereas the base will attack the hydrogen. Alright, So that's basically it. There isn't too much to SN2 reactions. There's no hydride shifts, there's no methyl shifts. Just make sure everything's small, not too bulky, and it's a concerted reaction. Again, the kinetics are going to be based off the nucleophile and the electrophile in this case. So the CH3O minus and whatever the hell that other electrophile is. I'm going to be lazy right now. What was it? Yeah, that wonderful thing there. It's not the point here. The point was the actual reaction. So make sure you practice. There aren't too many ways you can slip up on the SN2s. Just know that it has to be a strong attacker, some sort of alkoxide ion or the hydroxyl ion or something like that. Okay, cyanide. These are all strong nucleophiles. So practice. Thank you and have a nice day.